Hey guys, this video is going to be talking about inscribed angles and the relationships with inside circles. So in the previous lesson, we talked about what a central angle was. So just to recap, a central angle, very simply, is an angle whose vertex is at the center of the circle. So the key to take away from that in terms of this lesson is the vertex occurs at the center of the circle. That's what we call a central angle. What we're going to talk about today is what's called an inscribed angle. And pretty much it's once again an angle within inside a circle, but the key here is the vertex this time is going to occur on the circle. So vertex is now on a circle. So down the drawing below, the angle here on the left hand side represents a central angle, and the angle on the right side here represents an inscribed angle. And there is a distinct relationship between the two. But before we talk about that, the arc that is created from these angles is going to have a name. And so, for example, the arcs here that are highlighted in blue, we're going to call them the intercepted arc. And what that means by definition is an arc that lies on the interior of an inscribed or a central angle. And the endpoints are going to end up being on the angle itself. So the blue angles here we would call the intercepted angles of the inscribed angle, for example, or the central angle. The last thing I want to take a look at here in our vocabulary is a central angle very simply is just two radii connecting to one another. And secondly, an inscribed angle is containing chords. So one quick way for you to identify is not only by what their vertices are, the location of the vertices, but you can also look at the segments that actually create the angle. And so with that being said, what we have to talk about now is the relationship between a central angle and an inscribed angle. So the measure of a central angle is always going to be, as we talked about in the previous lesson, congruent to the intercepted arc. And so we take a look at that if we go over to GeoGebra here. And this central angle right here is 66 degrees and it looks like 0.12. This arc right here is also going to measure that. So this arc is also 66 degrees approximately when we look at it. So what we want to talk about right now is how an inscribed angle relates to the intercepted arc. So what is the relationship between an inscribed angle and its arc? And the best way you can do that is use GeoGebra. So I know this arc right here that I have measured is definitely 66 degrees. And again, here's how I can verify. If I take a quarter of my circle, it's 90 degrees. And there it is. It says 90. I move this to take up half the circle, and you can see that, hey, look, it's 180 degrees. So this central angle definitely represents this arc. So what I'm going to do is create an inscribed angle using these same 2 points on the circle. So first thing I need to do is I need to make a point on the circle to represent the vertex. Doesn't matter where I put it, I'll throw it there. Now I'm going to create a segment connecting, so a chord technically, right? Connecting from this edge of the arc to the vertex, and again I'm going to do one from here to here. And so before I go ahead and take the measurement, I want you to take just a few seconds to look at this and say, okay, what do you think this angle is going to be in relationship to this angle? And to make it maybe a little bit easier, I'm going to go make this a 90-degree angle, as best as I can, of course. There, I'll call that 90. So if that's 90, what do you think that's going to be? So it definitely isn't equal. We can definitely clear that up. But now the question is, what is this going to be? And if you look, when I move it, it doesn't actually change the angle. So no matter where I put this, it doesn't change what the angle is going to be. So let's go ahead and take a measure here. So I'm going to go click these vertices, and survey says 45.1. So the central angle is 90.2, the inscribed angle is 45.1. It appears to me that the inscribed angle is half of the arc. Let's test it by dragging this around a little bit. 136, 68.3. Okay, feels pretty good so far. 67, 33. So even if I move this around, look how that inscribed angles does not change being 33.97 degrees. So no matter what I do, the inscribed angle always ends up being half of what this arc is going to be. And that's exactly what we're going to jot down here. Measure of an inscribed angle is always going to be half the measure of the intercepted arc. And guys, that's pretty much the main purpose of this lesson. So really what we're going to spend the next couple minutes talking about are some theorems in relationship to this. Before I do that, though, I want to give you a secondary look at how this is proven. So I've proven it to you visually by looking at a GeoGebra and looking at measures. But I want to just show you here, looking at this situation. So I'm saying I want to prove that ABQ, which is this inscribed angle here, is equal to half of the arc AC. So we're going to do kind of an informal proof just for you to kind of view here and take note. But instead of calling it ABQ and AC, I know that we like to look at things algebraically instead. So instead, let's go ahead and call this x equals 1/2 of y. Y being arc AC and ABQ being x. So I basically want to prove that this y, half of this y is going to be the value of x. And so first thing I'm going to do is, well, since I know AC is going to be equal to y, why don't we make AQC equal to y? Because we know the central angle and its intercepted arc are always going to be congruent to each other. Well, since I know that, this AQB, I've drawn two radii in AQ and QB on purpose to create a triangle. And that means we know some stuff here. These two angles are linear pairs. And so if this is y, this just has to be 180 minus whatever this ends up being. Like if this was 60 degrees, I would take 180 minus 60 and say, hey, that's 120. Hence why I have that. So if this angle's x, this angle's 180 minus y, this angle up here, AQB, we actually know that. AQB is an isosceles triangle. Why? Well, because AQ and QB are both radii. And since this is isosceles, that means this angle has to be x, making these base angles. And something we learned earlier in this course says that the three angles of a triangle are going to add up to 180. So I can add this x, and this 180 minus y, and set that all equal to 180 degrees. This sets up our proof. So pretty much at this point now, we just have to do some algebra to solve everything. And so when I do all of that solving, I add the x's, make it 2x. I subtract the 180 over, hey, they cancel out and become 0. Then I add the y over, and I have 2x equals y, which is almost what I was trying to prove. Divide both sides by 2, and hey, I've got my winner. So this is an algebraic way to prove to you that this relationship has to exist. So we have a visual proof. We now have an algebraic proof kind of taken to this. Okay? A couple of quick theorems we're going to look at here. Before we do that, though, I want you to look at these two examples. So I want you to pause the video right now. Take a look at these. When you have had a chance to try these yourself, please unpause the video, and we will go over what the answers are going to be. Okay, so now that you've taken a look at this, we know that HF is going to be 84 degrees. And so they basically want to know angle G. So very simply, they're just asking you to show the theorem that we just talked about. If this is 84, this is going to be half of it. And half of 84 is going to be what? 42. So our answer is 42. We take a look at this next one. They want to figure out QR. So QR is actually this part up top here. Well, to figure that out, I've got to first find QT. And the reason I need to find QT is, well, QT and QR, I know together, they're going to end up equaling 180 degrees. How do I know that? Well, I know that RPT is half the circle. And so when I go ahead and take that, I am going to double 38, and I am going to end up with, I believe, 76 here. Okay? Well, now that I know that's 76, I can simply just take 180 from 76 and confirm that QR here has to be 104 degrees. Here are the couple theorems we're going to finish this video up with. So, number one, I know that AD is 124 degrees. So I'm giving that to you as a fact. Take a moment, pause the video again, and find the measure of AOD, find the measure of ABD, and find the measure of ACD. Now that you've taken a look at that, AOD is a central angle, so central angles are always equal to their arc, so that means this is going to be 124. ABD is an inscribed angle, and so I know that since it ends at A and it ends at D, that the arc that it intercepts is also AD. So ABD being an inscribed angle is just simply going to be half of that 124, which means it's going to measure 62. ACD is another inscribed angle, and it also so happens that it intercepts the same arc AD here. And so all three of these answers have the same intercepted arc of AD. First one was a central angle, hence why it was equal. ABD was an inscribed, why it was half, and ACD is also half, meaning it's 62. So what can we conclude this? Well, we kind of talked about it on GeoGebra. two inscribed angles of a circle that intercept the same arc, well, that means the angles automatically have to be congruent. So kind of a conclusion here is I could have told you right away that ABD and ACD were automatically going to be congruent to each other because they were both inscribed angles and they both intercepted the same arc. Taking a look at the next term here, number one vocab term at the top here, an inscribed polygon. So an inscribed polygon, we're going to call a polygon that when all the vertices, all of them, lie on the circle. So inscribed angle is vertice on the circle, or vertex I should say. An inscribed polygon is when all the vertices are on the circle. So basically this question says if AB is the diameter of the circle, what type of triangle is this going to be? Well, keep in mind that ACB, that angle right there, that angle is going to intercept the diameter, or half the circle. And we know that an inscribed angle is always half the circle. So if this whole arc right here is 180, that makes this guy right here have to be 90. Therefore, we can conclude a right triangle is going to be inscribed in the circle if and only if, so this makes this a biconditional, the hypotenuse is the diameter of the circle. So really what you need to take away from this page is that if the hypotenuse is a diameter, well then it has to be a right triangle. Those are basically the big picture items we can take away from this slide here. On the same token here, take a minute to pause this video. I want you to find these missing angles. Use the idea that all four of these angles are inscribed angles. So look at the arcs that they intercept. Now that you've had a chance to look at this, let's talk briefly about how we figure this out. I know that this is 95 degrees. I know that this arc that I'm drawing in green all the way around here is its intercepted arc, being that the angle 95 ends here and here, which means that green arc that I've just drawn for you is 190 degrees. Okay. Well, now that I know that angle X right here is intercepted by, let's draw that in yellow. I know its intercepted arc starts here, ends here, so it's pretty much the rest of the circle. So the 95 and the X have a special relationship. These two angles intercept the entire circle together. This green 95 makes 190, which means if I take 360 away from 190, that the yellow arc that I have drawn here is 170. Well, since I know that's 170 now, X has to be, in this case, half of that. And so we're going to divide that out and make it 85. Look at the relationship that X has with the 95. If we now know this is 85, I can simply add the 72, the 95, and the 85 together. Why can I do that? Well, I know that all four angles of a quadrilateral add up to 360. When I add these three angles up, I get 252. When I subtract that from 360, I end up with a Y value here of 108. Again, if you aren't sure, pause this video for a minute to see if you can check this out yourself. But basically here, what we can conclude is that the X and the 95 are supplementary. The Y and the 72 are supplementary. And so our conclusion here is a quadrilateral is going to be inscribed in a circle if, and only if, so it's the biconditional again, the opposite angles are supplementary. So quadrilateral, these are the key words I'm highlighting. Quadrilaterals are going to be inscribed when their opposite angles are supplementary. And that leads me to our final question here in this lesson. And this is where we're going to end. And you're going to have this discussion in class and or on Canvas. What type of special quadrilaterals we learned back in the previous chapter can be inscribed in a circle? So we have our isosceles trapezoid, we have our parallelogram, we have our square, our rectangle, our kite, and our rhombus. And we can include regular trapezoid in there as well if you like. So think about all of those different polygons and which ones are going to be able to be inscribed in a circle. That concludes this video. Feel free to rewind and go back to anything you may have missed or may not understand. And please look below for your further assignments on Canvas.